last piece on solid set, I'd like to talk about environmental concerns. Solid set does have a couple of advantages in environmental concerns where we can use it for frost protection and we can use it for cooling. And in frost protection, we're basically taking advantage of the heat release when water forms from a liquid to a solid. At that instant, there is a heat of fusion released into the atmosphere and into the limb of the plant that's being warmed if it's forming ice on the limb, and we actually raise the air temperature in the conversion of a liquid to a solid when the water changes its shape or its form. Conversely, the exact opposite happens in cooling. When we throw that water up in the air and get it to evaporate from a liquid to a gas, it absorbs heat from the air to make that conversion happen. And in the process, it cools the air because it pulls heat out of the air. So we get a cooling effect. Now, it works with cooling very well when we have very low humidity, because we get maximum evaporation occurring, and with maximum evaporation we get maximum heat absorption, which gives us maximum cooling. So the drier it is, the more cooling we can get. It's the same effect that a swamp cooler works on. It's the whole concept of a swamp cooler in a building. Works the same way, except now we're trying to do it to the atmosphere out in a field. Very effective. When you have real high humidities, not very effective. Low humidities is when you usually have the really hot days. It works very well. Now, the twist on volume of water gets to be a little specialized. When we're doing frost protection, we have to have the entire field operating continuously. So that requires a very large volume of water pumped, very large pump station, very large main line, and the ability to turn every block on in a field all at one time. So the controller has to be specialized to be able to do that also. It takes a very large capacity. In cooling, we only have to do it about a quarter of the time to get the effect. So about 15 minutes on, 45 minutes off can be very effective for cooling. We don't have to keep the water on continuously. So we can break the field into 4 blocks and just keep cycling around 4 blocks for cooling. So we don't need near the pump capacity, near the mainline capacity for the cooling effect. We're going to spend an hour just on those issues later on in the quarter. On to drip. The first characteristic feature of drip is the fact that it is very, very small exit points. Because of the fact we have very, very small exit points, we have to have extremely good filtration. And I just brought a inline filter to give you an idea of a type of filtration. This is just a screen filter, the most simplistic style. And this would not be a fine enough mesh for most drip systems, but it gives you an idea of how they're made. And it's simply the water comes in to the center, comes outside through the screen, and in the process of coming out through the screen, any of the large particulates get caught inside. And then when I want to clean it, I just flush it out the center. Or vice versa. The water could come to the outside, go to the center and out the system, and then I would clean the outside of the screen. They're made both ways. This mesh can vary according to the need of the system. And this mesh is about 50 grids to the inch. So there's 50 little screens, outlets to the square inch. You can get it as fine as 200 mesh. So any particle has to be pretty tiny to pass through 200 grids to the inch. And every emitter has a specific filtration value that is required. Some emitters might only have 60 mesh requirement. Some might have as much as 200 mesh requirement, and anywhere in between, just depending on the type of emitter that you're working with. This is kind of a handy one. It's see-through. You can actually look through it and observe the water quality and the filtration when it needs to be cleaned.